Swayam Prabha. Digital India. Educated India.
Welcome to the next session on Pharmaceutical Organic Chemistry Paper 3. In the Unit 2, we are studying about stereoisomerism Part 2. In the Lecture 3, we will be studying about conformational isomerism. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayamprabha, MHRD, New Delhi. The topics that will be covered in this session includes conformational isomerism, the definition of conformational isomerism, why we have to study about conformational isomerism, what is conformational isomerism, all those details we will be studying. We will also be studying about the conformations of ethane and butane, the smallest molecules. We will also be studying about conformations of cyclohexane, and we will finally be studying about the ring flip in cyclohexanes. Let us now study about conformational isomerism. We will just go through the glossary, the new terms which we will be encountering in this particular session. Dihedral angle, gauge arrangement, staggered arrangement, torsional strain, chair, boat and twist boat conformations, axial and equatorial bonds. So we have earlier seen that stereoisomerism can be categorized into two major categories. One is the configurational isomerism, another one is the conformational isomerism. In the configurational isomerism, we have already studied about RS nomenclature and enantiomers, diastereomers, etc. We have seen earlier. And in the conformational, even geometric isomerism also we have studied. So in this particular session, we will be focusing more on the conformational isomerism part. So this is a brief overview of what is conformational isomerism. We will be studying most of the things in detail in this particular session. So we have atrope isomerism, that is a subset of conformational isomerism. We have open chain conformational isomerism and cyclic conformational isomerism. These are all the three major categories. And the open chain can be further divided into eclipsed arrangements or partially eclipsed arrangement or staggered arrangement. And the staggered arrangement can further be divided into gauge arrangement where 60-degree angle is the dihedral angle, and anti-arrangement where the dihedral angle is 180 degrees. So we will see about these things in more detail. So let us start with the simplest thing. What is a dihedral angle? So dihedral angle is basically defined as, in a chain of atoms, that is ABCD, there are 4 atoms required in this particular case. The dihedral angle is the angle between the plane containing the atoms ABC, that is 1, 2, 3 atoms, and that containing BCD, another set of atoms. So here 2 atoms are common for both the planes. So in the first one, BC is common for the ABC plane, and in the second one also BC is a common atoms. So this is the crucial thing when we talk about dihedral angle. When we talk about simple bond angle, we only have 3 atoms A, B, C. So the B is the center, and based on the center, what is the angle created by A, B, C is the bond angle. In the dihedral angle, we have 1 more atom. Instead of 3 atoms, we will be having 4 atoms. We will take the simple example of ethane conformation, and we will just look at what is a dihedral angle. And to look at the dihedral angle, basically we can do the 2-dimensional representation of the Newman projection, and this is much easier to view. Now I will show how to look at the dihedral angle in the 3-dimensional way. So we talked about ABCD 4 atoms. Now I am putting them as the numbers 1, 2, 3, 4. 1, 2, 3, 4. So these are all the 4 atoms. and based on these 4 atoms we are going to see what is a dihedral angle. The angle between 1, 2, 3 is the bond angle that we already know. Now there are two planes. We are talking about two planes, that is ABC will form in one plane. That means 1, 2, 3. These 3 atoms will form one plane, and 2, 3, 4 is another at 3 atoms which will form another plane. So the angle between the 1, 2, 3 atoms plane and the 2, 3, 4 atoms plane is the dihedral angle. So we are actually now looking at this is the ethane conformation, which is the anti or the staggered conformation. We will see this little bit more in the soon. Now we are only looking at the dihedral angle. So in this particular case, we are actually rotating the molecule like this way to see how the dihedral angle actually changes. So now this is the bond which is common to both the atoms. So now when we say, here you see the small a, small b, small c and d are there. These are all the 4 atoms, and for our convenience I had put the big numbers 1, 2, 3, 4. So the number 180 is actually the 180 degree dihedral angle which is made by the planes. That is 1, 2, 3 will form one plane, 2, 3, 4 will form another plane. So the angle between these two is 180 degree. In other words, these two are in the same plane. So if I rotate this particular bond, now you will see the angle changing. So this 180 degree, just watch here. When I rotate the molecule, so this is going in the counterclockwise direction. So when it is going in the counterclockwise direction, the angle becomes negative. Okay, so this is the negative dihedral angle, and if I rotate the molecule in the clockwise direction, now you see the angle is in the positive direction. So this is how we can say whether the molecule is actually being rotated in the clockwise direction or in the anti-clockwise direction. So this is one way of identifying how the dihedral angle is crucial for looking at the conformations. Now this is 170. I will now take it to 145. Okay, so this is another arrangement. I will make it to 0 degree. So when I make it to close to 0 degree, let us look what is the dihedral angle's rotation and how the molecule actually is seen. So when we do the 180 degree dihedral angle rotation, we are actually moving from the anti-arrangement to completely eclipsed arrangement. Okay, so this is one type of the way we can actually look at the molecule, and from the dihedral angle we can say we had moved from the anti-arrangement to eclipsed arrangement. So we will also be studying what is this eclipsed arrangement, because if you look at here in this molecule, the back hydrogen is completely masked by the front hydrogen, and these two hydrogens, if you look at, the left hydrogen is completely masked, the behind hydrogen is completely masked, and if you look at the right one, the behind hydrogen is completely masked. So this is what is called the completely eclipsed arrangement, and here the dihedral angle is 0 degree. So if I rotate it to, if I rotate the torsional angle to 160 degree, okay, and if we look at the molecule, this is similar to the anti-arrangement or the staggered arrangement, and this is also called as the Gauch arrangement. We had seen 60 degree dihedral angle. So this 60 degree dihedral angle is for the 4 atoms when they are in the different planes. So 1, 2, 3, these are in one plane, 2, 3, 4, this is in another plane. So the angle between this particular plane and the second plane is 60 degree. This is positive or plus 60 degree. So this is where we talk about the gauge arrangements based on dihedral angle. So by rotating the dihedral angle, we can make different arrangements. So if I go to 120, and if I look at the molecule from the front, this leads to eclipsed arrangement. So by looking at the dihedral angle itself, we can very well say whether we are having a eclipsed arrangement or a gauge arrangement or a staggered anti-arrangement. So all these things can be studied using dihedral angle. So this is very important for amino acid studies and protein structures and other thing. When we talk about, we do need to know what is the dihedral angle and how to study the dihedral angle. So we have seen how to calculate the dihedral angle using the three-dimensional representation. So we will move to the next one. So this entire chart talks about how or what are the different terminologies used in defining the different arrangements, different conformational arrangements. When the dihedral angle is 0 degree, we say this is the eclipsed arrangement, and when the dihedral angle is 180 degree, we call that as the anti-arrangement. So we have two types. We have actually seen that what is positive and negative. If it is in the clockwise direction, that is called the positive, and if it is in the anti-clockwise direction, that is the negative one. So these two things we have already seen in the three-dimensional representation. The same way, if the groups, the two groups which we are actually focusing on for the dihedral angle analysis, if they are in the 90 degree angle, that is from plus 90 degree to minus 90 degree, the entire arrangement, if these two groups, say for example, if you look at this one, both the R groups are on the same side. So the angle between these two things is basically 0 degree. So this is what is called the syn arrangement. And when they are in the opposite side, that is 180 degree, that is what is called the anti arrangement. So these two also, depending on the substituents or the groups which are involved in the dihedral angle calculation, we say they are syn or anti. And clinal and periplanar are the other two terms which generally people use. We generally are very comfortable, or we are in the elimination reactions, when we say periplanar arrangement is required, anti-periplanar arrangement is required for elimination. So what is this anti-periplanar? Anti means basically that is in the bottom half. So the main group and the leaving group, these two are in the anti-periplanar arrangement. In other words, they are in the anti-configuration. Anti is basically in this particular case 180 degree, because periplanar means any angle from plus 150 to minus 150 or plus 30 to minus 30. So this area, in the top area or the bottom area, these both areas are called as the periplanar arrangement. So this is in the anti, that means 180 degree it is there. The two groups which are leaving in that particular case are in the 180 degree angle. So this is anti, and they are in the same plane, so periplanar. So this is how, based on the dihedral angle, we can actually use syn, anti, clinal and periplanar, positive and negative ways. So these are all the various conventions that are used in conformational analysis. All these are based on the dihedral angle or the torsional angle. Now, if we take the conformational analysis of acyclic systems, basically we can take ethane as the simplest case. In the case of ethane, the R is basically hydrogen, the back R is also hydrogen. So we will have less number of conformations in this particular case, in the case of ethanes. But if it is a butane, the R group is a methyl group, the second R group is a methyl group. So we can have all the different types of arrangements as shown here. So I will take, for convenience, first we will take only the ethane molecule. So these two are the eclipsed conformation. So the angle is 0 degree. So the dihedral angle is 0 degree is basically the eclipsed conformation. And when the dihedral angle is 60 degree, that is a gauge arrangement. And when we go to the partial eclipse, that is 120 degree, basically this is again going to be the completely eclipsed one in the case of ethane. And this hydrogen and this hydrogen, when they are in the 180 degree, we call that as a staggered or the trans arrangement. And the same way, if we go in the negative angle rotation, then we will also go to the partial eclipse, which is actually normal eclipse for hydrogen and the gauge arrangement. Then finally we will come back to the eclipsed conformation. So that means the back carbon or the hydrogen or the groups attached to the back carbon are rotated in clockwise direction. So the front one is kept fixed or it is not at all disturbed. So based on this only, we actually rotate the bond, that is the carbon-carbon bond, which is actually behind here in this particular Newman projection formula. So by rotating that, we are actually making different conformations. So these are all the different conformations by the dihedral angle changes. So now let us talk about what are conformational isomers. So we have seen it is a form of the stereoisomerism, which we already know. And these isomers are interconverted by rotation about formally a single bond, that is sigma bonds. So that is what we have seen. The carbon-carbon sigma bond is rotated, and how the atoms on the each carbon are placed is called the conformational isomers. As we have seen various conformations for the ethane molecule, the eclipsed conformation, partially eclipsed conformation, they may have similar or different energies. Whenever there is an eclipsing conformation, they are actually repel, the electron cloud repel, and they will be having higher energy. And many of the other conformations will have lower energy. And basically, if you look at the ethane molecule, which is the simplest one, there is a rotational barrier. And this is an important factor for the interconversion of one conformer to another conformer. So if you look at the eclipsed conformation and the anti-conformation, the groups are far away. We will be looking at a little bit detail. So there is a difference in energy between each conformations. And when we look at cyclohexane, which is a cyclic system, the ring flip actually is an example of conformational isomerism. And when we study the potential energy difference with respect to different conformations, that study is called conformational analysis. So these are all some of the fundamentals about conformational isomers. So now the next question is, why do we need to study conformational isomerism? So this is an important question we have to answer before we delve more into conformational isomerism. So the conformational isomerism is studied or it is used to explain the product selectivity in a particular chemical reaction. This can also help in explaining the mechanism. As we mentioned earlier, for the elimination reaction, anti-periplenarity is required. So that can be explained based on the conformational analysis. And the rates of the reactions can also be explained based on whether the bulky groups are in the eclipsed conformation or a gauge conformation, and under what condition they favor that particular type of reaction. So they all can be explained based on conformational analysis of the molecules. And conformational analysis also plays an important role in the rational and structural based drug design. So this is another important aspect where conformational analysis is used. In 1969, the Nobel Prize in Chemistry was awarded to Derek Barton and Art Hassel because they have contributed a lot to the development of the concept of conformation and its application to chemistry. So we can say conformational isomerism had received a Nobel Prize because this is one of the important isomerism which is used for drug development and other reaction mechanism analysis, etc. We will now go into the detailed study of conformations of ethane. We already know that hydrogen molecule, the bond rotation and other things are happening at a rapid rate. And these are happening at room temperature itself. That is, the rotation about the carbon-carbon single bond is very rapid. Even though we say it is very rapid, the CC bond rotation has a rotational barrier of around 2.875 kilocalories per mole. Although this value is very small, still there is a rotational barrier for the rotation about the carbon-carbon single bond. Why there is a rotational barrier can be explained based on simple facts. See, there is a steric repulsion in the eclipsed conformation, which is called the destabilizing effect, and an enhanced stabilization of the staggered conformation due to hyperconjugation. So we can now look at the ethane molecule to see what are these two effects. Now, before that, we talked about rotational barrier, energies and other things. So how do we actually find out the strain energy in a particular system? So basically, the heat of formation is a crucial thing which is used for studying or understanding strain energies in a system. So what is heat of formation? Heat of formation is of a compound is the enthalpy change when the compound is formed from its constituent elements. Say for example, if we talk about ethane's heat of formation, ethane is formed from 6 hydrogens and 2 carbon atoms. So when these compound, the constituent atoms are joining together, so how much energy is required for their formation is called the heat of formation. This can be calculated by two ways. One is theoretically we can actually calculate what is the CH bond energy, what is the CC bond energy. From that we can actually calculate what is the theoretical heat of formation for ethane, and we can also do the same thing by combining two carbon atoms and we try to identify what is the heat of formation by experimental methods. In the case of cyclic alkanes, the difference is often referred as the strain energy. So when we do the theoretical calculation and the observed one, there is always going to be some difference between the theoretical one and the observed one. So based on that, whatever is the difference is called as the strain energy. Now we talked about rotational barrier. So ethane has 3 hydrogen eclipsed atoms. So in this particular eclipsed conformation, if you look at this hydrogen and this hydrogen, these two hydrogens and these two hydrogens, they are all in the eclipsed conformation. So there is a repulsion between these two hydrogens electron cloud. The same way there is a repulsion between the electron cloud of these two hydrogens, and for this hydrogens also there is a repulsion. So when there is a repulsion, they don't want to stay in that particular arrangement. So that means this particular conformation is quite unstable conformation. So the destabilizing energy for that is around 1 kilocalories per mole. Since 3 hydrogen interactions are there, the total destabilization energy is equivalent to around 3 kilocalories per mole. That is what we had seen. It was 2.875 is the value we have seen, which is close enough to 3 kilocalories per mole. And in the case of propane, if you look at, there is a methyl group and a hydrogen. So this is again a eclipsed conformation. In this particular case, there is a interaction between two hydrogen, because in this eclipse conformation, this one set of hydrogens, there is another set of hydrogens, they both interact, they are in the eclipse conformation, and there is one hydrogen and the methyl group is also there, which is having little bit more destabilization energy. So two hydrogen interaction and one hydrogen methyl interaction is there, due to which the destabilization energy is little bit more in the case of propane, which is around 3.4 kilocalories per mole. And in the case of butane, we have again hydrogen, here again hydrogen. So two sets of hydrogen interactions are there, and one set of methyl interaction is there. the methyl-methyl interaction is a little bit more destabilizing because the methyl group occupies more space than the hydrogen atom. So that is the reason in the completely eclipsed arrangement, we have around 3.8 kilocalories of moles destabilization energy. When we talk about the destabilization energy, so there should be some reference with respect to that, the energy difference we are actually calculating. So for our calculations, what we assume is one of the energy is considered to be 0 or the starting point. So in the eclipse conformation, we can assume that this is having 0. Whatever is the energy it is having, we assume that that is 0 energy, and the staggered arrangement will have some particular energy. So the difference between these two energies are called as the destabilization energy. Since the staggered arrangement is more stable one, so this will be having a negative energy compared to this one. So this eclipse conformation will have high energy, whatever may be the value. It may have X kilocalories of mole energy. The same way the staggered arrangement will have Y kilocalories per mole of energy. The difference between X and Y is this particular destabilizing energy. We can actually look at the different conformations of ethane using either the Sahar's method or the Sahar's representation. The Newman projections are shown here. So basically the difference between these two hydrogen is called as the dihedral angle, and the back carbon is behind, which is not seen, and the front carbon is shown here. And in this particular case, if you are looking from the top side, these three hydrogens are shown here, and the other three hydrogens are shown here. So one of the hydrogen is at the top, two are on the sides. So one of the hydrogen is on the top, two are on the sides, and in the other case, the one of the hydrogen is at the bottom. So here again, these two hydrogens are pointing downwards in the first carbon. In the second carbon, these two hydrogens are pointing upwards. So here you see these two hydrogens are pointing upwards, and this hydrogen is pointing downwards. So that way we can actually look at the molecule. This is the anti-arrangement, and in the staggered arrangements or the anti-arrangement, we can see all the 6 hydrogen atoms. Whereas in the eclipse conformation, we can see only 1, 2, 3. So this is the one we have seen in the 3-dimensional representation also. Let us talk about what is the torsional strains. So we know ethane can have infinite number of arrangements, and each of these various arrangements are called as the conformations. There is intermolecular strain present in a molecule due to non-bonded interactions between two eclipsed atoms or groups. So this is what we were talking about, the electronic cloud repulsion between two eclipsed atoms or groups, because they are non-bonded, because those two electron clouds are not bonded to each other. So this is a non-bonded interaction or a steric interaction. This strain is actually responsible for the existence of rotational barrier. So when there is a steric repulsion between two groups, they don't want to be in that particular arrangement. So that restricts the CC bond rotation, that is the free CC bond rotation is not possible because of this particular steric repulsion. And this is also called the Pitzer strain, torsional strain, and bond opposition strain. So when we talk about torsional energy, we have something called the energy required to rotate around the CC bond in ethane. So there is a CC bond in the center. We are rotating this backside carbon atom. So the energy required to rotate this is basically called as the torsional energy. And when we plot the potential energy diagram of different conformations, so this is the high energy conformation, that is the eclipsed conformation. We have anti or the staggered conformation. This is the most stable conformation. So if you look at the potential energy graph, these are having low energy compared to this one. So the energy difference is the one we are talking about, the torsional energy or the rotational barrier. So this instability of the conformation is called the torsional strain. So in most of the cases, all the atoms and the molecules tend to be in the most stable conformation. So here we wrote the Sahar's projection for the ethane molecule, and this is the Newman projection. So when we look at here, this is the eclipsed conformation. These two hydrogens are eclipsed. So if we rotate the molecule towards this way, we can see these two hydrogens are being eclipsed, and we can also write the another conformation of ethane like this in the Sahar's representation or in the Newman representation. So in the Sahar's representation, these two hydrogens are pointing towards upwards. So that is what we see here. These two hydrogens are pointing towards upwards, and this hydrogen is pointing downwards. So here again we see this hydrogen is pointing downwards, and in the back carbon, one hydrogen is pointing upwards, two hydrogens are pointing downwards. So that is what we see here. One hydrogen is pointing upwards and the two hydrogens are pointing downwards. So when we move that to the Newman projection, so here we see all the 6 hydrogen atoms are there. In this particular arrangement, the distance between these two hydrogens are optimal. The same way the distance between these two hydrogens are optimal. So all the hydrogens are actually optimally placed from each other. So this is the most stable conformation. In this particular conformation, there will be least strain or steric strain between these two hydrogens. Whereas in the eclipse conformation, these two are in close proximity, these two are in close proximity, these two are in close proximity, so there is a repulsion. So this is how we can study about the different conformations. So we know this is the eclipse conformation, this is the staggered arrangement or staggered conformation. When we talk about butane, the conformational isomers of butane, we have different conformation corresponding to energy minima called the conformers. So we have also studied about diastereomers and enantiomers. So this arrangement, the gauge or the skewed arrangement, that is what we call in the case of butane. The difference between butane and ethane is in butane, 2 hydrogens are replaced from ethane. So ethane has 6 hydrogens. 2 hydrogens are replaced with the methyl groups to get the butane molecule. So when we talk about conformational analysis of this one, we have partial eclipsed and the gauge arrangements for butane. So this methyl is at the top, one of the methyl is on the left hand side. In this particular arrangement, the methyl is at the top and the other methyl is on the right hand side. So the dihedral angle between these two methyl group is around 60 degree. This is in the positive direction, or it is a plus 60 degree, and in this case this is a minus 60 degree. So these two are the skewed or the gauge arrangements for butane, and there is a mirror image relationship, object mirror image relationship between these two isomers. So we call these two as the enantiomers. And when we talk about, because they have the same molecular formula, and when we talk about the staggered arrangement, each staggered arrangement and the skewed or the gauge arrangement is basically diastereomeric ratio, because these two, the arrangements are basically different. This is the skewed arrangement, this is the anti-arrangement. The methyl groups are kept far away here, the methyl groups are in close proximity. So there is no object mirror image relationship between the staggered arrangement and the gauge or the skewed arrangement. So these two are basically diastereomers. So this way we can also use enantiomer diastereomeric terms for the conformational isomers. So when we do the conformational analysis of isomers of butane, we have different conformational isomers. The energy diagram, this is the potential energy diagram, which is plotted against the degree of rotation, that is the dihedral angle is given here. So based on each dihedral angle difference, the energy goes from the highest energy, which is the completely eclipsed conformation, to the first gauge conformation. We have these two methyl groups are still in proximity, so there is little bit of steric repulsion between these two methyl groups. So but this is having less energy compared to the completely eclipsed conformation. So the energy is little bit lower in this particular case. When we rotate the molecule another 60 degree, because we started from 0 degree, that is a completely eclipsed, to the 60 degree, which is the skewed or the gauge conformation. So in this particular case, we are rotating in the plus direction, that is the positive direction, and another 60-degree rotation leads to partially eclipsed arrangement. So this is having little bit less energy compared to the completely eclipsed conformation, because the completely eclipsed conformation has a much higher energy, whereas the partial eclipse conformation has little bit lower energy, because the interaction between the methyl group and the hydrogen is not very high compared to methyl-methyl interaction in A. So we rotate another 60 degree, we reach the 180 degree. So this is the anti-arrangement or the staggered arrangement. In this particular arrangement, both the methyl groups are far away from each other. So there is no steric interaction between both the methyl groups, as well as the methyl hydrogen interaction is also very low. So that is why this conformation, that is the anti-conformation, is having the lowest energy of all the conformations of butane. And when we rotate another 60 degree, we reach the 240 degree. Here we have again the partial eclipsed arrangement. So that is why this energy rises again. And when we rotate another 60 degree, we have the gauge conformation. In this particular case, the energy is little bit lower compared to the partially eclipsed one, and we rotate another 60 degree, that is 360 degree. When we rotate, this again goes to the completely eclipsed conformation, so it has the maximum energy. So by this, by rotating the dihedral angles, we can actually make different conformations of butane, and this study, the energy, the potential energy of each conformation with respect to dihedral angle is called the conformational analysis. So in this we have 1, 2, 3, 3 troughs are there, 1, 2, 3, 4, 4 peaks are there. In other words, we have basically A, these two are one and the same. So we have the eclipsed conformation having the highest energy, followed by partial eclipsed conformation which is having little bit lower energy, followed by gauge conformation having much lower energy, and the completely anti-conformation having the least energy. So this is how we can actually study the different conformations of butane. So here the actual values are given. So the anti-conformation is having minus 5.2 to minus 6.9 kilocalories per mole basically. So this is, we are assuming that the completely eclipsed conformation is having zero energy. So that is the assumption we are making. So with respect to that, this conformation is having more stabilization. So whenever we say a negative energy, in the case of potential energy, the negative energy is the most stable one. The positive energies are quite unstable one. So in this anti-conformation, we have negative energy minus 5.2, which is the highest of all the three values. So in other words, this is the most stable conformation having least energy. So the stabilization and the energy are always inversely proportional. The most stable conformation always has the least energy. And in the case of gauge, we have partial, these two methyl groups are close enough. The same way here again, these two methyl groups are close enough. This is a gauge arrangement. So in this case, the energy difference is, they are somewhat stable compared to completely eclipsed one. Here the energy is somewhere between minus 4.4 kilocalories per mole. So this is how we can actually study the conformations of different isomers of butane. Let us move to the next one, which is the conformations of cyclohexane. So far we have studied about the open chain system, ethane and butane. Now we will move on to the cyclic system, which is cyclohexane. Let us look at various factors that affect conformations. In the case of cyclic system, we have additional strains called the angle strain, because here this is a cyclic system. So we have a particular angle strain present in various cyclic systems. So the any deviation from the normal bond angle is accompanied by an angle strain, because in the case of carbon, it is a tetrahedral carbon. So the bond angle is around 109 degree 45 minutes. But in a cyclic system, we have to actually push the carbons close enough. So they generally deviate from the ideal bond angle of 109 degree. So this difference, whatever is the difference, is called the angle strain. And in the case of non-bonded atoms, because we are forcing two atoms to come close in the case of cyclic system formation, so there is always going to be some non-bonded interaction. And in the case of eclipse conformation, we have seen high ethane and butane, the eclipse conformations are destabilized because of the non-bonded interaction. The same way in cyclic system also we have non-bonded interactions. So this is also called as van der Waals strain or steric strain or Prolog strain. And we already know the torsional strain which is present in ethane and butane. The same is also applicable for cyclic systems. So that is the torsional strain. But one additional thing which is present in cyclic system is the dipole-dipole interaction, which actually favors a particular conformation. So these are all the various conformational factors which affect the cyclic system's conformation. Now here we have drawn the cyclohexane structure. So this structure is basically called as like a person sitting in a chair. So this type of conformation is called the chair conformation for cyclohexane. Now we already are familiar with this particular structure of ethane. So here we have all 1, 2, 3, 4, 5, 6. In 6 places we have hydrogen. So this is the staggered arrangement for ethane, and we can extend the same to the case of cyclohexane as well. So in the case of cyclohexane, if you look at, there is a carbon here, there is one carbon behind, there is a carbon here, there is a carbon here, there is a carbon behind, there is a carbon here. So if you look at how many carbons are there, 1 behind 2, 3, 4 behind 5, 6. So we have 6 carbons are present. So nothing but this is the cyclohexane arrangement. This has 2 staggered ethane like arrangements. So this is what is the chair conformation of the cyclohexane. So this is the most stable conformation, because in this particular arrangement it is following the staggered arrangement, which is the most stable conformation we already know for ethane. So in the case of cyclohexane also, this is the most stable or the preferred conformation for cyclohexane. Along with that chair conformation, there are also various type of conformations possible for cyclohexane. One is called the half chair conformation. Another one is a twist board. So if you look at, this is like a board and this is twisted little bit. So this is called the twist board conformation, and this is basically the normal board conformation. And there is again, in this particular case, the bond is going from left to right, from bottom to top. In this particular case, left to right, top to bottom. So this way we can have 2 different twist boat arrangements, and we also have other arrangement which is called as a chair conformation. So all these conformations will have different energy due to different non-bonded interactions, angle strains and other things. Here I am showing the space filling model for the cyclohexane. So this is the side view if you are looking from the molecule from the side. So this is the actual 2-dimensional representation of the cyclohexane with all the hydrogen shown here. The white balls are the hydrogen atoms, and this particular are the carbon atoms. If we are looking from the side, this is the view what we will see in the space filling model. And if we are looking from the top, we see 1, 2, 3 hydrogens, and we have 1, 2, 3, 4, 5, 6 hydrogens. So the 6 hydrogens are actually pointing sideways, and we have 3 hydrogens pointing towards ourselves. So this is how we actually look at the molecule from the top. This is again a space filling model. Let us move to the next one. We have the boat conformation. So in this particular boat conformation, this is very similar to the eclipsed conformation of ethane. So we already know in the eclipsed conformation there is going to be lot of strain between these two hydrogen atoms. The same way in the case of boat conformation also, we have a lot of interaction between these two hydrogens and these two hydrogens. So this particular boat conformation of cyclohexane is the most unstable one, and we also have something called the flagpole bonds. So this also is important thing for the instability of the boat conformation. So this is quite unstable conformation for cyclohexane. This is similar to the boat conformation. Here we see there are 1, 2, 3, 4. 4 protons are very close proximity, and these two hydrogens, if you look at the front one and the back one, here again the front one and the back one, here these two. So all these are in the eclipsed conformation. So because of this eclipsed conformation, this particular arrangement is having more strain. If we go back to the space filling model of the chair conformation, here if you look very carefully, 1, 2, 3. So these three hydrogens are not eclipsing each other. So that is the reason here we do not have any eclipsing interaction present in this particular chair conformation. So that is why this conformation is the most stable one. Whereas in the case of boat, we have here again eclipsing conformation, here eclipsing conformation, here eclipsing, here eclipsing. So we have 4 eclipsing conformation, due to which this molecule is little bit unstable. So because of that instability, what happens is the boat conformation wants to move away from that eclipsing conformation. That leads to the formation of twist boat. So these two hydrogen which are in close proximity want to move apart, and these two hydrogens, since they are very far away, it doesn't matter if they come closer or not, there is still not going to be much steric interaction. Whereas in this particular case, there is a lot of interaction, that is a flagpole interaction we have seen. So due to that, these two hydrogens want to move away. So during that process, what happens is the normal boat getting converted into a twist boat. So that means the distance between these two hydrogens become little bit more. So the distance between these two are like 1.83 angstrom is changed to 2.5 angstrom. So these two hydrogens are moving from 1.83 angstrom to 2.5 angstrom, that is 0.7 angstrom away from each other. So that gives little bit stabilization to this particular arrangement. So that's the reason from the boat conformation, the twist boat conformation is having little bit better stabilization and low energy. So this is the flagpole one. So in this particular flagpole one, as we have seen here, there is a lot of interaction between these two hydrogens. So this is quite unstable. So the boat conformation as shown here is the most unstable conformation. So as we have seen earlier, this flagpole, they are in close proximity. They are pushed. One is pushed to the left, another one is pushed to the right. So in the twist boat conformation, what happens is this one of the hydrogen is here, the other hydrogen moves away from that. So due to this, the energy gain is there because the repulsion is reduced because of these two hydrogens are moving apart. So the twist boat conformation gets much better energy compared to the completely eclipsed one, that is the boat conformation. So if you look at the potential energy diagram for the various conformations of cyclohexane, the chair conformation is having the most stable of all the conformations. So this is having the least energy, and the half chair conformation is the most unstable one with very high energy, followed by the twist boat conformation, and the boat conformation is actually having little bit better energy than the half chair conformation. So that way what we can see is the various conformational isomers of cyclohexane and their energy difference. So this is taken as the reference. So with respect to this, the half chair is having 11 kilocalories per mole high energy. The twist board conformation, although it is a little bit better than the half chair conformation, still it is having high energy with respect to the chair conformation, that is 5.5 kilocalories per mole. And if we look at the board conformation, so from the chair conformation, it is 5.5 plus 1.6. So that means 7.1 kilocalories per mole high energy. The board conformation is going to be 7.1 kilocalories per mole high energy than the chair conformation. So this is how we can actually study the various potential energy diagrams of cyclohexane's conformations. Let us look at what is an angle strain and the torsional strain. The angle strain is basically caused by the bond angle deviation from 109 degree 5 minute, and the torsional strain is caused by the eclipsing CH bond on adjacent carbons. So these are all the two major strains that are present in cyclohexane. Now let us look at equatorial and axial bonds. So in cyclohexane we have 6 hydrogens that are pointing towards the sides, and 3 hydrogens lie in one plane and the other 3 lie in another plane. So here you see these 6 hydrogens are called equatorial hydrogens. They are actually shown here in the red one. So 1, 2, and the back we have 3, 4, 5, 6. So there are 6 hydrogen atoms. These are pointing sideways. So these hydrogen atoms are basically called as the equatorial hydrogens, and we will see the three-dimensional representation for this one and the axial one. Then we can compare how these are actually present. So the next one is the axial bond. Here again we have 6 hydrogens, 1, 2, 3, 4, 5, 6. This is the olive green color shown. These 6 hydrogens are basically 3 are lying above the plane or in the top, and 3 are lying below. These 3 hydrogens lie in the same plane, and these 3 hydrogens also lie in the same plane. So 3 are pointing upwards and 3 are pointing downwards. So these are called the axial bonds. We will look at the three-dimensional representation of this molecule to understand what is equatorial and axial bonds. So here is the cyclohexane molecule in the 3 dimension. So we say it is a chair conformation. So you can see this is the chair which we are talking about. So you can rotate this, and this way also in some places they write the chair conformation. So this is like a zigzag arrangement, and if I rotate a little bit this way, so we see like a chair. Or if I rotate this way and the bottom, so there is a carbon. If you look very carefully, let us see here what are all the different carbons. This is 1, 2, 3, 4, 5 and 6. 6 carbons are there, and out of these 6 carbons, 3 carbons, 1, 2 and 3, they lie in one plane. 1, 2, 3. These 3 lie in a different plane. So we have 2 different planes onto which the carbons are actually situated in the cyclohexane molecule. And we were talking about axial and equatorial hydrogens. So 1, 2, 3. These 3 hydrogens are pointing upwards. So this is what is called the axial hydrogen. And we have 4, 5, 6. So there are total 6 hydrogens, 3 of them pointing upwards, 3 of them pointing downwards. So these are all the axial hydrogens, and all of them lie in a same plane. If you look very carefully, so this and all the 3 hydrogens lie in one plane, and the bottom 3 hydrogens also lie in the same plane. So that way we have 2 planes onto which the top 3 hydrogens and the bottom 3 hydrogens lie. And we also have 6 different hydrogens called the equatorial hydrogens. So let us look at what are the 6 equatorial hydrogens. we have 1, 2, 3, 4, 5 and 6. So these 6 hydrogens are basically pointing either upwards or downwards, and they are actually pointing to the sides. So these are all the 6 hydrogens which are basically pointing towards the side, and of this 1, 3 and 5, these 3 hydrogens lie in one plane, 2, 4, 6 will lie in another plane. So out of the 6 hydrogens, let us look at how many of them are actually pointing slightly upwards and slightly downwards. So this hydrogen, the first one is pointing downwards. The next one is actually pointing little bit upwards. The next one is pointing downwards, pointing upwards, pointing downwards, pointing upwards. So that way what happens is each alternate hydrogens are either pointing upwards or downwards. So these 6 hydrogens are the equatorial hydrogens. So when we do the ring flip, they actually change their position. The axial one will become equatorial and the equatorial one will become axial. In all the cases, an unsubstituted cyclohexane, we have 3 axial hydrogens pointing upwards, 3 axial hydrogens pointing downwards, 3 equatorial hydrogens pointing upwards, and 3 equatorial hydrogens pointing downwards. So that is how all the 12 hydrogens are present. So we have seen the three-dimensional representation or the arrangements of equatorial and axial bonds in the case of cyclohexane. Here is a space filling model for the equatorial bonds. The hydrogens in red color is the equatorial one. This is a space filling model. We are looking from the top, and this is we are looking from the side. So this is how the space filling model of cyclohexane is represented. The same way, if you look at the axial bond, the olive green color represents the hydrogens in the axial orientation. So we are looking from the top, we could see the 3 from the top, the remaining 3 are at the bottom. And when we look at from the side view, we can see at least 3 here very clearly, and 2 are seen here, 1 is behind, so we cannot see that. So this is how the space filling model for the cyclohexane looks. Now this is a wireframe arrangement, because we are now going to see some of the different ways how the cyclohexane can be represented. This is a wireframe model, and this is called the ball and stick model. This is a 2D representation, the normal representation. And this is a space filling model. Here the axial bonds are shown in red color and the equatorial bonds are shown in white color. So you can see here the red one are all representing the axial hydrogens. The white ones all represent the equatorial ones. Now another important thing is the ring flip in cyclohexane. So how do we know what is the ring flip and how it happens? You all know, or you have played seesaw when you are young age. So if you remember the seesaw, this is precisely the ring flip of cyclohexane. So this way you can actually look at when one person goes down, the other person goes up. Precisely that is what happens in the case of cyclohexane ring flip. So in one place, the one person is at the top, another person is at the bottom. When we do the ring flip, this person goes up and this person comes down. So the same way, the two-dimensional representation of cyclohexane is given here. This person is pointing downwards, or he is down, so that is how this is pointing downwards. And this person is pointing up, so he is at the top, so this carbon is at the top. So this is how we write one of the cyclohexane chair conformation. And when we do a ring flip, so this person actually goes up and this person comes down. That means this carbon goes up, this carbon comes down. So that is how we can actually write the ring flip in cyclohexane. This is a two-dimensional representation, and this is how you can easily remember. Take one up, take one down. So here we will be looking at some of the equatorial axial bonds in the cyclohexane. So if we look at 1,2 arrangements, the axial and the equatorial arrangement is basically cis. In other words, the axial hydrogen and the next equatorial hydrogen, they are both cis to each other. That means they are pointing either upwards or downwards. So they are in the same side. If you look at the second carbon on the other side also, this equatorial hydrogen is again pointing upwards. So what we can say is 1,2 axial equatorial arrangement is always cis arrangement. So this is one type of cyclohexane where this carbon is pointing downwards. We are doing a ring flip. Then what happens is this axial bond becomes like a equatorial bond. So the red color one, the hydrogen, whatever we are showing here in the axial one becomes the equatorial one. This equatorial one becomes actually the axial one. So this is how the ring flip actually happens. So this is the carbon number 1, that is the carbon number 1 here. So here the equatorial becomes axial, the axial becomes equatorial. In the second carbon, the equatorial becomes axial, the axial becomes equatorial. So this way when we do the ring flip, what happens? Still this axial hydrogen and this equatorial hydrogen, they both are in the same side. That means they are pointing upwards only. So they are still cis. So when you do a ring flip, this axial equatorial 1,2 arrangement remains cis before the flip and after the flip. So this is what you have to remember whenever you do a ring flip. The axial hydrogen may change to equatorial hydrogen. That is possible. The equatorial hydrogen may change to axial hydrogen. That is possible. But their relative positions remain the same. If 1,2 substituents are cis in one conformation, doing a ring flip will always keep the same 1,2 substituents in the cis conformation only. So by doing the ring flip, the cis-trans isomerism does not take place in the cyclohexanes conformation. So this one always you have to remember. Let us look at the 1,3 substitution now. So here we have the carbon number 1 having axial and equatorial bonds, and we also have the 3 carbon. In this particular case, the axial hydrogens are pointing on the same side. So they are cis arrangement. And if you look at the axial and the equatorial one, they are in the trans arrangement. One is pointing upwards, another one is pointing downwards. So the adjacent, that is 1,3 arrangement, both axial groups are in the cis orientation, and in the 1,3 arrangement, the axial equatorial arrangement is always trans. When we do the ring flip, as we have seen earlier also, the axial group still remains at the bottom, so they are again cis. The axial equatorial remains trans, so they are always trans. So the ring flip did not change the 1,3 substitutions, that is axial equatorial change does not lead to cis trans changes. And if you look at the 1,4 substitution, so here again axial equatorial groups are in the cis orientation, axial groups are in the trans orientation. So this way you can always remember. So this way you can always remember what is the 1,2, 1,3 or 1,4 substitutions in the case of cyclohexanes, and whether they are the axial equatorial bonds or axial bonds, you can actually follow very carefully. Let us recap what we have studied so far for the equatorial and axial bonds in the case of cyclohexane. If there is groups in 1-2 position, axial equatorial or equatorial and axial is always cis, and axial axial or equatorial equatorial is trans for the 1-2 position, and for 1-3 the axial axial or equatorial equatorial is always cis, and axial equatorial or equatorial axial is trans, and in the case of 1-4 substitution, axial and equatorial or equatorial and axial are cis arrangements, axial and axial or equatorial and equatorial are trans arrangements. So by this table we can actually identify what is the substitution patterns in the case of cyclohexane, and we can also identify whether the axial and equatorial bonds are on the same side or on the opposite side. The ring flip does not change this particular arrangement. In summary, let us recap what we have studied so far. We have studied about conformational isomerism, its definition, what are conformational isomers, why we have to study about conformational isomerism, what is their application, all those things we have studied. We have also studied about some basic compounds, basically the conformations of ethane and butane. What are gauge conformation, what are staggered conformation, what is anti-arrangement, what is eclipsed and partial eclipsed arrangements. All those conformational analysis we have studied. We also have studied about conformations of cyclohexane, what is an axial bond, what is an equatorial bond, what is ring flip. So all those details we have studied. We also have studied about the relative conformational positions of axial and equatorial substituents 1-2, 1-3 and 1-4 substituents. With this, we conclude this session on conformational analysis and conformations. Thank you.